But like, Lulu's Hermes, I really like it because I don't have to follow a lot of rules. But once you get to a higher stuff, it's like very few position specialties. You get a package that thing, but a lot of it is more. A lot of them are very bureaucratic. And you can probably, so you have to kind of, whereas military, you don't have that, and it's okay. Way less than the building. So I know you don't make it.
How we all doing? Good? Good. Looks like Zoom's up and running. Looks like the camera's working. And it's recording for those of you who want to look back on this lecture with fond memories of what goes on today. So today we're continuing our story of charges. And we're continuing our story of charges, talking specifically about the forces that exist between those two charges. Last time we had a problem that involved 3 charges, right? And they were all on a line and worked out perfectly fine for the case of the one-dimensional lines, charges existing all on the x-axis. But we might want to expand out. We might want to expand out to multiple dimensions, not necessarily 3 dimensions. We'll just stick with 2 dimensions. 3 dimensions is easy enough to expand out into, but 3 dimensions is a lot harder to draw, so we'll stick with 2 dimensions. And when we talk about 2 dimensions, it becomes important to start defining our coordinate system. And the common way we define our coordinate system is with an xy axis, y is out positive, and x is positive to the right. Yes? So anytime we say that we have a positive value, a positive x component, right, we're saying it's to the right, and a positive y component means upwards. And we're going to start having to deal with these multiple components. Let me give you an example that is going to be similar to what you might see today. If we had 3 charges, we'll say whatever these 3 charges are, they exist in this 2-dimensional space that is the board. We want to figure out what types of charges these are. So someone give me an example. Do we want this to be a proton or an electron? Electron, sounds great. Proton or electron? Electron. Got 3 electrons. That's great. So we have 3 electrons in this coordinate system. And once we start dealing with multiple electrons, especially multiple charges in general, especially like we did last time, it becomes helpful to number our charges. So we'll number them. We'll say this is charge number 1, charge number 2, and charge number 3. Just to have it simply, I didn't realize this doesn't cover the entire board. A little inconvenience. All right, so we have our 3 charges and we want to apply Coulomb's law. Coulomb's law tells us about the forces that go on between these charges, right? Pairs of charges feel a Coulomb force between them. So if we care about the forces on charge 2, let's consider charge 2, right? That's the one we're interested in. What does charge 2 see? Charge 2 sees charge 1 and it creates a force, right? A Coulomb force going to the right. Yes?
Yes.
Okay. Now we'll label this. We'll label this force that 2 feels from 1, force 2 comma 1. And it's just a way to bookkeep to tell us that this is the force charge 2 says from charge 1. It's just a convenient way to remember what's going on. What are we talking about? How do we differentiate these things? And we have force 2 comma 3 going upwards, right? We have a positive x force and a positive y force. Yeah? Not too bad. But what if I ask you about the net force on this problem, right? All of this other stuff has been the same as doing a one-dimensional case, right? Still just dealing with forces, still calculating using Coulomb's law, K, Q1, Q2 over R squared. But now when we combine these forces, we now have to consider the fact that they are not lying along the same axis. So if we wanted to know the net force, how do we figure that out?
Tip the tail.
What's that?
Tip the tail.
It's tell you have to add vectors in a special way. You can't just say F12 plus or F21 plus F23. You have to do one of these methods of vector addition that we've learned so long ago. So we can take F23, right, represented by this vector. We can move this over, right? And our net vector, our net force is going to be the vector that starts at the tail of our first vector going up to the tip of our second vector, right? So the blue vector is what's representing our net force, F net. You remember this, right? Just going through a quick refresher. Feel comfortable with this? So how do we find that magnitude? You know, we can find F21. F21 is easily found with Coulomb's law. Okay, Q2, Q1 over the distance R between 2 and 1 squared, right? That's easy enough to figure out. Same thing for F23. Just gonna put quotation marks saying you use the same methodology. Yeah, you switch out those 1s for 3s, but everything else stays the same. And once you have these two values, how do you figure out the magnitude of your net force?
You add the vectors, and then
You add the vectors. How do we do that mathematically, though?
you just put one on top of the other, and put the x values together and the y values together, you get the third vector, and then do x and y values. And
Okay, so you're saying let's add them up component by component, right? We can look at these, right? These just tell us magnitudes. We can write them in vector form. We can say that F21 is equal to K Q2 Q1 over R21 squared. And we can say that this is in the positive I hat direction, the positive X direction. Yes, using unit vector notation. The other one is positive Y vector. You say your net force. So, right. Similarly, we have F2, 3 equal to K Q2, Q3 over R23 squared. See if that catches on the camera. It does not. Try out the track. See if that'll work.
Oh, wow.
No.
Oh, yeah, I can see everything.
It's showing a little too much. Why? Oh, there we go. I think that looks better. So we have F2, 3 represented by the J hat. That's our Y vector. We can say our net force F net is equal to, I don't want to write it. F21 I hat plus F23 J hat. Right? Because those are our entire forces, those are our entire X and Y components. Nothing shocking there. But what if we wanted to know how much force, how many newtons of force is this, right? What is the magnitude? We know our X and Y components, how do we find the magnitude?
They're just a squared plus b squared equals c squared.
We have a nice right triangle here. Use Pythagorean theorem to figure out what's our net force is going to be, what the magnitude of it, right? So Emilio is telling us this is the vector form. He's saying these are the components of our new vector. Figure out the magnitude, you just use Pythagorean theorem. Pythagorean theorem, adding these components in quadrature. Are there any questions, thoughts, comments? Seems easy enough, right? The story gets a little bit more complicated. I'm sure you guys remember when you have to deal with forces that are not necessarily entirely in the X direction, not necessarily entirely in the Y direction. Let's say we have a force. Let's say we're concerned with electron number 1. Electron number 1 has 2 forces on it, right? It's going to have a force from 2. F1 feels by 2. going to the left, so that's a negative I hat, negative x component. But what direction is the force that is feeling from 3 going? Negative x and positive y. It's going to have both an x and y components. F, 1, 3, going to be upwards and to the left. So how do we treat that vector? How do we deal with that? You break this into its 2 components. This has a y component, right? F1, 3, y has an x component. F1, 3, x. And now you take your x components, add them together. Now you have your x component and your y component. You can do Pythagorean theorem. So you can deal with these off-axis forces, right? And this is how you deal with 2-dimensional problems. This is how you dealt with it back in 2500, right? You guys remember doing a lot of problems like this, I assume. Yes? No? Vaguely? Do you guys feel comfortable with this, or do we need to stay a little bit further on this? Who feels comfortable with vectors? All right, fantastic. Looks like majority. So today you're going to be faced with a problem. Based on Coulomb's law, that is a 2-dimensional problem. You're going to be given several protons that are arranged in sort of a similar fashion to this. You're going to be asked what the net force on those are. Be sure to work on that problem at the bare minimum before you leave class today, because if you need help with vectors, we need to know now. If we need to stay longer on vectors, we will, because that's an important part of this class. And it's important to know, for us to know if you guys are comfortable with them or not. The other things we're going to be working on today, we're going to touch a little bit more on waves. Right? So we saw waves. And we said waves have several characteristics to them, right? They have a spatial characteristic, length, a characteristic length called the wavelength. Our wavelength represented by the Greek symbol lambda. Yeah? You remember this? Ringing some bells? We also said that waves have a characteristic time. And this characteristic time we call the period, represented by t, right? And it just tells you how quickly is this wave going to repeat whatever motion it's going to go in. There's this other characteristic called frequency. Frequency is just the inverse of period. Yeah. And wavelength, period, and frequency all combined in a specific way to tell us something about how fast the wave is traveling. Wave speed, the subscript speed. I'm probably going to drop the subscript pretty soon. Just going to assume I'm talking about the wave speed when we talk about a speed associated with a wave. And our wave speed is what? Well, it's distance over time, lambda over t, or lambda times frequency. Both are equivalent ways to figure out wave speed. And we did this for like waves on an ocean, right? But the waves that we're concerned with in this class, in electricity and magnetism, the waves we care about are electromagnetic waves. And electromagnetic waves, these are your light waves, your radio waves, your gamma rays. These all have a special characteristic, and this special characteristic is that they have a constant speed. When we say that that constant speed, represented by the letter C, is the speed of light. It's 3 times 10 to the 8 meters per second. A hair slower than that, but we can round to 3 times 10 to the 8 meters per second. So this is how fast waves travel in a vacuum. I'm gonna try.
Oh,
Sorry, I tried to reduce glare on the camera. I don't think it's gonna happen though. So waves travel at a certain speed. It travels at this constant speed, and that means if you know the wavelength of an electromagnetic wave, since speed is a constant, you can automatically get frequency. Frequency is just speed over wavelength, or you can figure out time period. So for any electromagnetic wave, if you know lambda, you automatically are given free of charge. You're given. Okay, that's a little better. You're automatically given free of charge the other part of the wave, the yet unknown part. Another interesting thing about light traveling at a certain speed. Light travels at a certain speed, and this gives us a great way to measure distances, especially very, very large distances. And you might have heard of the distance, the light year, right? We talk about galaxies, we say these galaxies are light years away. Light year is the distance that light travels in a single year, as the name would imply. To figure out how far exactly that is, well, we know what the speed of light is, right? And we know that speed is always distance over time. So, you want to know what 1 light year is? 1 light year is going to be the speed of light, c, right? Converted to units that involve years, not seconds. But 1 light year is c times 1 year. To figure it out, I think it's something like 14 trillion kilometers or something like that. Very, very large distance. Today you'll be doing some stuff involving that light year value. But this is what makes electromagnetic waves really nice, is that you do only have to deal with 1 speed, as long as your light is in a vacuum. Once we start talking about light traveling through materials, materials slow down light a little bit. But for the purposes of right now, we're dealing with light in space or light in the open air. All travels at about 3 times 8 meters per second. Any thoughts, questions, concerns, ideas, statements? All right. One more concept I want to introduce to you guys, right? So we did some stuff with charges, looking at some stuff with waves. And the last thing that we're going to touch on today, the last thing we're going to build a little bit further is in our knowledge of circuits. And in our knowledge of circuits, we've learned about this idea of current, right? Current goes through resistors, right? Feel like this is okay. We know current travels through circuits, but our simple circuit that we looked at last time, it's just a resistor and a battery, right? We might want more complex circuits, want something more interesting than this. So what are we going to do? Well, the next most interesting thing would be to probably add another resistor. Right? So you just throw another resistor in there, and we notice something occurring. Our resistors, if they're in the same circuit, then we're going to have a point which we have 2 incoming parts of the circuit combining into just 1 wire, right? So we imagine that our 2 resistors come together, combine at this point, and continue to the battery. We must have that if we have more than 1 component. And this has a special name. We call this a junction. Now, junctions aren't any sort of special area. They need to follow the laws of physics, and one of the laws of physics says that matter cannot be created, matter cannot be destroyed, right? And that is true for the charges that are being carried throughout our circuit. So if we have a current represented by this red arrow, we'll say this is current 1, I1. This current is just a bunch of charges moving through our circuit. Going through the bottom resistor, we might have a second current, I2. These do not have to be the same values. We can have different values of current going through each of these resistors. And then these two currents, these two flowing charges, right? They're going to meet up at this junction, and when they meet up at that junction, they're going to combine and continue along the path as I3. And since the charges must be conserved, that means every bit of current that enters the junction must also leave the junction. Does that make sense? Anything that comes in must go out. We can write this out using a formula. We can say that current going into a junction is equal to current out. Simple equation, right? Current in equals current out. What comes in must go out. In this case, our current in, what is supplying the current to the junction? That's I1. And that is I2, which I use green for. I stay color coordinated. That is equal to I3. So if we have 1 amp going through the top resistor, 2 amps going through the bottom resistor, that's 3 amps that must be leaving. This is what's known as Kirchhoff's junction rule. I think it's 2 amps. Kirchhoff's junction rule. What comes in must go out. Any questions about this? Yes.
Does a voltage split and go through both resistors with the same amount of voltage go through both?
So it depends on how we arrange our resistors. In this case, when we arrange our resistors side by side like this, then they're both going to have the same voltage. We imagine that this is like a 9-volt battery, right? Both of these resistors, there's nothing between them and the 9-volt battery, right? Since there's nothing between them and the 9-volt battery, there's nothing that's going to be split. Now we can arrange resistors or components in a way that will split voltages, and we'll get to that. Just taking one step at a time. Making sure we get every single part down before we move forward to the next. Any other questions? You okay about this? Is there a question in the back? I let you guys bring a cheat sheet, but I'm not going to be giving you formulas. I'll give you constants though. So Coulomb's constant you'll be given, speed of light you'll be given. If you want formula though, you have to write it down. Yes. I give you an example test. I mean, I'm giving you a lot of in-class problems, man. These in-class problems are going to be like building up to what you'd see it on the exam. If I have time, I'll make a sample exam, but I don't make any guarantees. Any other questions? Thoughts, comments, concerns? See if this works. So this is our classwork for today. It's also on Canvas as of, I think, 20 minutes ago. Yeah, it is on Canvas. So we're going to be working on this. Again, you're going to see some wave questions. Yes, question in the back. 3B from last week? That was 3B. Oh, the proton and the electron that are just side by side? Yeah. I'll come by and I'll help you individually while everyone else gets started on this. Sound good? Yeah. Any other questions? Thoughts, comments, concerns? Yes. I did post it on Canvas. It's right Right up here, LA session times. Any other questions?
Yeah, was there a limit on how many we could go a week?
Now you can go to all of them if you want. You got that much free time. Any other questions? All right. Find those students are getting- Trying to get that one. First out.
Determine what the direction of the force is in each of the previous given bases. So if the two particles produce a force, what direction is that would be the direction that is out.
Oh, okay. So we do have to make sure.
Yeah. Oh. I'm sorry, you shut them off. Oh, this isn't today. Yeah. Let's see. Let's move on. So we have that. I think that's what we- given the range of- So we- that range of prices, right? So we have one-
Well, he said, well.
You're aware of the moment, so. Is it in just do